Alright, this lesson that we're looking at is part of the stoichiometry unit, and there'll be some learning goals that we're going to try and establish by the end of this video lesson. A big thing to make sure you do when going through a lesson like this is to take the time to write the questions out. So make sure you hit pause, write the questions out, and then you can pause it as I go through certain sections just to make sure that you're understanding as we go. So what we're going to look at first is our first learning goal is I can calculate the carbon footprint of a smelting reaction. Smelting reactions are whenever you take an ore, which is typically a metal combined with oxygen, or sometimes metals combined with sulfur that you find in the ground, and you react them with carbon, typically coal or graphite. What that does is it removes the oxygen off the metal to produce you a solid form of the metal, and then typically your byproduct would be carbon dioxide if it's an oxide, or if it's a sulfide ore, you would get sulfur dioxide. Before we jump into it, though, I just want to draw your attention to some look-fors. These are things that the teacher looks for whenever a question's being done. If you follow these look-fors, you're ensuring that you're doing the questions properly, and if you ever want to assess your work or get a peer to assess whether you're doing questions correctly or not, this is what you would look at. So as you go to do any stoichiometry questions, my class and I co-constructed a bunch of things that we thought was really important to make sure we do whenever approaching a question like this. So one of the first ones was, and this is a biggie, is you need to make sure you write down the given info in the question using the variables and values. So if you're given mass and molar mass, make sure we write them down. An example right here. And another big thing is always use your units. Okay, always show them. Next, you want to write out what you're looking for. So if this question is asking you to find the number of moles given a certain mass and molar mass, then you would write the variable n with a question mark. That lets you know that that's what you're looking for. Another big thing, your next step, is typically to write out your formulas. And if you need to rearrange the formulas, it's a good idea to show that work. This allows the teacher to see what your thought process is. So here's an example right here, where say we use the formula for moles, which is N is equal to M over MM, mass over molar mass. Say I want to try and determine what my mass is, and I'm being given moles and molar mass instead. I show that I just cross multiply the molar mass up and actually show this work, and then the teacher can figure out exactly what your thinking process is there. Another big thing is to substitute the correct numbers into the proper places. So if you were given moles and molar mass, then you would make sure you sub your moles in here and your molar mass in there. Pretty straightforward. Typically when students make mistakes, a lot of times this is one of the areas where they make mistakes. So if you're assessing your peers' work and you notice that they put the wrong numbers in, or they put them in the incorrect place, you can make a comment on that. Another big thing, and this is sort of like housekeeping, but it's a good idea to keep all the equal signs lined up in a row, and you'll see that in the examples that I showed you. And it just helps to keep the work nice and clean, and it's easy for the teacher or the peers or yourself to go through and see what the work is being done. And then if there are any errors, it's much easier to pick out where the error was. Was it an error in thinking? Was it an error in inputting the numbers? Did you use the wrong formula? Things like that. And that way it allows you to get some part marks, which are always nice. We need to show all work, especially when converting units. Say if you're given mass in milligrams to convert to grams. And always show your units, including when your units get canceled out, because that can a lot of times save you if you accidentally goofed up the formula and mixed it up by accident. Typically your units, if you keep them in when you do your calculations and you follow rules for math, you can figure out, oh hey, I did that wrong. Another big thing is if there's a chemical equation involved, it needs to be balanced. That's really huge. Now, I also had a student come up with this one, that it's good practice, a good idea to estimate before you punch your numbers into your calculator. And that's something that we can't actually see on the page, but that's super, super important, that we make sure that we do that. And that way, if your answer is supposed to be 32 and you get 32 billion, you don't just write the answer down. So you always try and take a look at your numbers before you start crunching them and use that good number sense to make sure you have a rough idea of what the question should generally, the answer should generally be before you punch the numbers in. Because in a high pressure situation like a test, it's very easy to mash the wrong number by accident on the calculator. So anyways, we're going to look at calculating the carbon footprint in a smelting reaction. So here's our smelting reaction right here. We've got alumina, which is aluminum oxide, and it's found in bauxite ore. And when we extract it, get into a white powder, and we cook it with some carbon, typically anthracite coal or graphite, and we get aluminum, metal, and carbon dioxide. So we're given a specific mass of alumina, and we've got as much carbon as we possibly need to make the reaction go. And we want to figure out how much carbon dioxide is being produced. So if the question asks for the carbon footprint, we're looking at the mass of carbon dioxide. Before we jump into the question, we need to start balancing. And we typically balance our metals first, but I just want to give you a little hint. And the little hint is right there. It's Al2O3. Now, we've got an odd number by our oxygen here and an even number by our oxygen there. When you see that, I find it's a good idea to first of all double that. So if I double 3, it becomes an even number, which is 6, which then means I have even numbers on both sides. Very easy to work with. So I've got 2 times 2 aluminum, which gives me 4 aluminum. And I've got 6 oxygen, 2 times 3, which is 6. So I'm going to need 3 over here. So 3 times 2, which is 6 oxygen there. I've got 3 carbon there. Okay, so pause, take a little second, make sure that you can do that. If you can, jump down to this other question down here perhaps and quickly balance that one out. And just pause here for a sec, try and balance it, and then I'll quickly put the answer up. Okay, so now what I'm going to do is I'm going to start to pull back the curtain here and show you how these two questions were tackled. So remember, first couple steps in doing a question like this, we write out what we know and what we're looking for. So I'm going to take you through quickly what was done. So I wrote down my initial mass, 500 grams, and I calculated the molar mass of my alumina. Because if I want to determine the number of, or the mass of carbon dioxide produced, I can't go from mass to mass. It doesn't work that way. But the chemical reaction tells me the ratio of the number of units of each chemical in the reaction. So apparently 2 units of alumina makes 3 units of carbon dioxide. So if I had 2 chemical units of alumina, I would make 3 molecules of carbon dioxide. But I'm working with 500 grams of alumina. So in order to go from mass to the world of molecules and chemical units, I need to use my molar mass to determine the number of moles, because moles bridges the world of mass and molecules, or mass and atoms, or mass and chemical units, because 1 mole of anything has the same number of particles in it. 6.022 times 10 to the 23rd, which is Avogadro's number. So in order to determine moles, I take my mass of my substance divided by my molar mass. And you can see the work I did here. So alumina is, I got a molar mass rounded up to 27, and there's 2 of them, so I multiply that by 2. Oxygen has a molar mass of 16, there's 3 of them, so I multiply that by 3. And I get my molar mass 102 grams per mole. So if I had 102 grams of alumina, I'd have 1 mole, which is 6.022 times 10 to the 23rd units of alumina. But I don't have that many grams. In fact, I have more than that. I have 500. So I take 500 grams, divide by 102, and I get 4.9 moles of alumina. So now what I do is I look that I have a ratio. I have a ratio between alumina and carbon dioxide. That ratio is 2 to 3. So I should have a little bit more moles of carbon dioxide than I have of alumina. Bigger number, smaller number. So what that means is I take my number of moles, I multiply it by 3, then divide by 2. That number should be bigger. So my moles of carbon dioxide, I take my moles of alumina, multiply it by 3, divide by 2, and lo and behold, I have a larger number. So I'm on the right track now. Okay, so apparently I'm going to have to just quickly move this down for a second, and I'll grab this and erase it and move everything back up. There we go. Okay, so now you can see the rest of the work. So I determined my number of moles of alumina, of carbon dioxide, sorry, 7.35 moles. And then I found my molar mass. Notice I worked down this way, went across, and then I working right back up, kind of like the U form. And I like keeping my work like this because everything sort of lines up nicely. My moles always line up, my molar mass lines up, my mass lines up. So following a bit of a pattern. Anyways, determine my number of moles, determine my molar mass of carbon dioxide. So there's 1 carbon, which is atomic mass of 12, 2 oxygens, atomic mass of 16. Put them together, you get the molar mass, 44 grams per mole. So if I had 1 mole of carbon dioxide, it'd be 44 grams. Now, if I want to find my mass, it's my number of moles times my molar mass. And so I take my moles, my molar mass, multiply them together, ran out of room, but still okay, and I get 323.5 grams. So 500 grams of alumina nets me 323 grams of 0.5 grams, sorry, of carbon dioxide in order to get that aluminum out to make some pop cans or whatever you're going to make with it. So let's take a look at the carbon footprint of smelting iron. Iron's used to make steel. So we're going to look at taking a ton of iron 2 oxide and smelting it to make some iron. And we want to know what the carbon footprint of that is. So first, or sorry, in this case, we want to see if I made a ton of iron. How much carbon dioxide would I produce? So let's go through this question here. My mass is 1,000 kilograms of iron, which is 1,000,000 grams, or 1.0 times 10 to the 6 grams of iron. And that's how much I want to make. Now my molar mass of iron is really simple. I just find the atomic mass of iron and I plop that in. Notice, even though there's a 2 there, I do not multiply that by 2. Alright? Now if it was something like Fe2, then you would have to multiply it by 2, but it's just Fe by itself. So 55.8 grams per mole. So if I had 56 grams of iron in my hand, I'd have 1 mole. But obviously I have way more than that. So I take my mass divided by my molar mass, so 1,000,000 divided by 55.8, and I get 1.79 times 10 to the 4 moles. Now my molar ratio between iron and carbon dioxide is a 2 to 1 ratio. So that means I should have half the number of moles of carbon dioxide as I have of iron. 2 to 1, 2 to 1. So I took my moles of iron, divided by 2, and I got that. My molar mass of carbon dioxide, 44. If you're in my class, you're probably going to have that memorized pretty soon. Again, to find mass, it's moles times molar mass. So I have my number of moles, multiplied by my molar mass, had a little bit more room this time, which is good. 3.94 times 10 to the 5 grams. So that would be 39,400 grams, or 39 kilograms. So that's how we do those two questions. In this first one, I was given a reactant and tried to figure out how much product I would make. In this one, I was given one of the amounts of products and need to determine how much of the other product would be made. So now for this next set of questions, what we're going to do is be asked to find how much carbon dioxide is produced again. However, I'm given specific amounts of each reactant, and I have to determine which of the reactants is the limiting reagent. So this is the learning goal. I can determine the limiting reagent and use that, the limiting reagent, to calculate products formed in our reaction. So let's take a look here. Oh, before we start to pull the curtain back, we have to remember to do one thing. Balance the equation. So if you want to pause here for a second and then try and figure out how to balance it, and then I will show you the answer. Okay, we've got one oxygen here. Remember, if we have an odd number, what should we do? We should always make it even, multiply by 2. So there we go, which means I'm going to need 4 of these. Okay, 4 silver, and then it turns out that my carbon and carbon dioxide already balanced. Don't have to do any more than that. Alright, so I have a balanced equation. Now it's just a question of going through and solving. So what I'm initially going to do is start to get information for my silver and my carbon, my silver oxide and my carbon. So I'm just going to pull back the curtain a little bit here. Don't worry about this stuff right now. We're going to get to it. So my first step is to determine the number of moles of my silver oxide and my carbon. So I have 200 grams of silver oxide and I have 32 grams of carbon. Now we don't know how many moles of each of that they are, but we do know that there's a molar ratio of 2 to 1. So I need to have 2 parts of this for every 1 part of that once we get to moles. Not necessarily mass, but in moles. So I determine my molar mass of silver oxide, 2 times 108 for silver, plus 16 times 1 for my oxygen, 232 grams per mole. My molar mass of carbon, of course, is just 12. So my number of moles of silver oxide, and we can see this is going to be a small number already. It's going to be 200 divided by 232. Estimate, you know that this is smaller than that, so you're going to have a decimal, which is 0.86. We have more carbon than the molar mass, so 32 divided by 12 is 2.67. Now we can see right away that I should have twice as much silver oxide as I have carbon. That's my ratio. Do I have that here? No, I don't have nearly enough silver oxide to use up all of the carbon. I would need twice as much of this for my silver oxide, and I don't have that. Alright, so because of that, my limiting reagent is my silver oxide, and I put a therefore limiting reagent, or sometimes we put them up here, whatever. So now what that tells me is that I can only use my limiting reagent, moles, to determine my unknown moles, which is going to be carbon dioxide. So I look at my ratio, and this ratio is also 2 to 1. So I should have twice as many moles of silver oxide as I have carbon dioxide. So I'm just going to pull back the curtain here and show you that calculation. So moles of CO2 is equal to my moles of silver oxide divided by 2, 0.43 moles. And we can now get rid of that and look at the calculations. So just like the other questions, I know my moles, know my molar mass, multiply them both together, and I have my mass. So if I react 200 grams of silver oxide with 32 grams of graphite, I will get 18.9 grams of CO2. I will use up all of the 200 grams of silver oxide, but I will definitely have some carbon left over, a lot of carbon left over, in fact. And you could, if you want to, go ahead later and figure out how much carbon you would have left over, because if you knew that this is a 2 to 1 ratio, then we would have only used 0.43 moles of the 2.67 of the carbon. So we would have still just over 2 moles of carbon. We'd have 2.24 moles of carbon left over. We could figure out very easily what mass of carbon would not have reacted. But we'll save that for another question. So now let's take a look at another limiting reagent question here. This one's a little trickier because I don't give you the balanced equation. What we have is a reaction where we have some iron 3 chloride reacting with dihydrogen sulfide, and we're making some HCl. We want to determine the mass of hydrochloric acid produced. We know that the other product is going to be iron 3 sulfide. So our first step in this question is to come up with a balanced equation. And so I'll pull back the curtain a little bit there. So my balanced equation is we've got our iron 3 chloride and our dihydrogen sulfide making hydrochloric acid and iron 3 sulfide. And I now have to go and balance everything. I've got 2 irons here, I need to put 2 there, which is nice because it takes that odd number of chlorine and makes it even 6 chlorine, so I need a 6 here. And then I'll need to multiply this by 3, my dihydrogen sulfide, to give me 6 hydrogen, but it also gives me 3 sulfur. Now I know that I've been given my masses, and I've been given my masses of my 2 reactants. So before I go any further, I'm going to just quickly determine the molar masses of everything that I'm looking for in my question here. That way, get it done and over with. So I just did it in this little space here. So I determined the molar mass of iron 3 chloride. You can take a look, make sure, check your work, make sure you got the same number I did. Found the molar mass of dihydrogen sulfide, and I found the molar mass of hydrochloric acid. So once I have that done, that's my intermediate step to go from mass to moles. Easy stuff now. Bob's your uncle. We can whip through this really quickly here, and we'll pull back the curtain, and hopefully you're starting to see the patterns in how we approach these questions. So I take my masses, my molar masses, and I find moles. Alright, moles always m over mm. So 90 over 162.5, 52 divided by 34. So I determined that I have 0.55 moles of iron 3 chloride, and I have 1.53 moles of dihydrogen sulfide. Now my ratio between these two guys is 2 to 3, and I've written that out here. So what I need to do is I need to see, do I have enough of this to make that? And just looking at this right now, 0.55 is pretty close to just a third of 0.153. So I don't even really have to do a lot of math, although I showed you how I would do that right here. but I can tell right away that I don't have nearly enough of this. I need to have 2/3 of 1.53 moles of iron 3 chloride. So I could take this number, multiply it by 2, divide it by 3, and I should get, if I do that, when I do that calculation, it should be the same here. It turns out that if I take this, multiply it by 2, divide by 3, I get a number bigger than 0.55. Check it yourself right now. You'll find that you will get a number bigger than that. Your number will be around close to 1. And so because of that, I don't have enough of this to react all of this. So this is my limiting reagent. So I now look at my ratio between my limiting reagent, iron 3 chloride, and HCl. And it turns out that it's a 2 to 6 ratio, which is really a 1 to 3 ratio. We get that to its lowest form. So I just simply start to do my work. Oh, and I did this again here. So just give me one quick second, and I'm going to move this. That way I can highlight this, get rid of it, and move this back up. There we go. Okay, so now I know my ratio of my limiting reagent to my product. It's a 1 to 3 ratio. That means for every 1 mole of my limiting reagent, iron 3 chloride, I need to have 3 times that for my hydrochloric acid. So therefore, moles of HCl is equal to moles of iron 3 chloride times 3. So I take 0.55, multiply it by 3, and I get 1.65 moles. I now know my number of moles. I've determined my molar mass. I multiply them together, and I determine my mass of HCl. So that is the extent to which we will be doing our stoichiometry at this point for our first test on it. Like I said, good suggestion is to go back, try these questions on your own, write the questions out, and then just see if you get the same numbers that I do. And if you're not sure why, or you made a mistake, go back and listen to the video again and see how I got each section.